All right, so we simplified 21/14 to 3/2. We subtracted the exponents for A, B, and C, but the directions say only positive exponents. What's that supposed to tell us? Negatives go to the bottom. That's exactly what it tells us. So what we're going to do is keep anything that has a positive exponent on the top with a 3. That's the c to the 5th. But that's the only one that had a positive exponent, so we've got to put the a to the 5th on the bottom and the b squared on the bottom in order to make those positive. I suppose I'm recording. I'll leave it up to you. If you want to go take care of it and come back, you can do that. Otherwise, use me as an excuse and say, Mrs. Sear, I want you to stay for the practice test. Alrighty, number 3. Yeah. When we do the subtraction, everything goes on the top. And at that point, we say, okay, now we've got to move some of this stuff so that it becomes positive. The c to the 5th didn't need to move anywhere because it was already positive. But these two are going to have to go down to the bottom. Yep. Yep. Anything in number 3 fly out at you as I would do this first? Because this one has lots of different ways to do it. Lots of ways. Well, for me, I don't like those negatives. I'd rather not use them. And so what I was thinking was I would flip this to make that a positive 2. I think that would help a lot. So I would do this, 4n squared over 3m to the negative 3rd, and square the whole thing. That's just one of many ways to do this problem, but I think that helps a lot. Because then you look at it and you realize, well, now I can distribute the 2. I can give the 2 to everything that's up there. So I'll have 4 squared n to the 4th over 3 squared m to the negative 6. Well, I know what 4 squared is. That's 16, n to the 4th. And I know what 3 squared is. That's 9, m to the negative 6. But now I have a problem. You absolutely could. That would be another way to do this problem. In fact, when I got done, I was going to say you could just follow the order of operations and say, I'm going to bring this down here right now and make it positive. And then distribute the negative 2. However you want to do it, whatever you see, go with it. So how am I going to get rid of this negative for my m? Bring it to the top, exactly. So it'll be 16m to the 6th, n to the 4th, and that's just because we like to keep them in alphabetical order, over 9. The last thing to check would be, can we reduce 16 ninths? But we can't. So that one's done. You have to. Oh no, I'll give you credit if you did n to the 4th, n to the 6th, because it's still multiplication. Yeah. Right. So if you wanted to do this, you'd have to do it the right way. You'd have to say this is going to be 3 over 4m cubed n squared, all to the negative 2. Now you still have another negative, so you're going to have to flip it anyway. You know how I just flipped it right away? You could flip this again. It's going to give you the same answer and then square it. Because overall, we've got to flip the entire thing at some point. So you have that for the parentheses. All right, everything feeling okay about these 3? Do you need to explain, or maybe you were doing the problem a different way and you want to see that it works? All righty. Oh, square roots. Yeah, we can do that. What's the square root of 196? 14. And I would like the plus or minus piece on there. I know the book says we don't have to at this point. We really should think, hey, we are writing the square root down. We should put the plus or minus in there because that's a really good habit. Alrighty, square root of negative 121. See this? See people doing this. Why not? 2 slots. We're not getting a negative, right? So we're going to have to put no real solutions. It's not that it doesn't have a solution. We already know it's 11i. We studied that in Alrighty, this one says cube roots. And here's where you're going, oh my gosh, how am I going to do that? How would I take care of this without my power chart? Well, you get to use your calculator. So you go under math, and you see that number 4 has cube root. So you hit that, and then you put in negative 729, and you hold your breath and hope it's a perfect cube. Oh, look at that, it is, it's negative 9. 512 over 216. If I were doing this one, I would split these two up. Thinking, hey, the cube root of 512 has to be something nice. Math, number 4, 512 is 8. And the cube root of 216 is 6, but I want to make sure I punch all of this in so everybody can see all of that. And then I just reduce it. You could punch it in as one fraction. So you could hit math, number 4, punch in 512 divided by 216, enter math number 1, and it'll change your decimal back into a fraction. You get the exact same answer. But I think it's easier just to punch it in. So there's our nice perfect cubes. Should we put plus or minus on our perfect cubes? Can't do that. You've got to have square roots, fourth roots, sixth roots, eighth roots, and even roots for the plus or minus piece. So those shouldn't be too bad, right? Punch them in. Everybody knows where to get the cube root button. Next up, simplify each radical expression. Use absolute value symbols when needed. Oh, I remember these. We split this stuff up because we said the number part, that's going to be easy. We know what the square root of 144 is. But then we're going to need the square root of x squared, the square root of x squared, the square root of x squared, because I need 6 of them. Square root of y squared, 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 because I need 8 of those. And in the end, some people said, well, can't you just divide? So if you remember that, if you remember the shortcut, and you want to do that, and just realize this is a little 2 out here, and divide, you can do that. But the square root of 144 is 12, and we'll have x times x times x, which is x to the 3rd, and y times y times y times y, y to the 4th. And then we need to ask ourselves if we should be slapping some absolute value bars on something. Any of that need absolute value bars? The x to the 3rd does. Yeah, we've got square root, that's even, odd power answer. Right there. Y to the 4th is fine. That's number 7, we change colors here. Cube root of negative 216. I think I remember that one from the power chart. Cube root of a to the 3rd. Cube root of a to the 3rd. Cube root of a to the 3rd. Cube root of a to the 3rd, because I needed a grand total of 12. You remember the cube root of negative 216? Punching it in then. Math. Number 4. Negative 216. Negative 6. Negative 6, a times a times a times a to the 4th. Does that one need absolute value bars? Nope, it's not an even root. That was an odd root. So it doesn't need it. Oh my goodness. The 4th root of 3125. Seriously? 4th root of y to the 4th. Ooh, this one gets interesting. Because the next one would have to be the 4th root of y to the 3rd to get 7. And we're not going to be able to do that. That's going to have an ugly part. Then we've got the y to the 13th. So we'll have the 4th root of y to the 4th, 4th root of y to the 4th, 4th root of y to the 4th. And we're going to have one ugly 4th root of y. So we've got some pretty stuff and then some ugly stuff. Now, 3125, 4th root. Oh, I wrote y's in. Good gravy. I was thinking ahead of the y's. Instead of my x's, I put y's. Said x's and put y's there instead. Let's see. I'm thinking 5 to the 4th is probably a good bet. 625. And that's because this has a 5 in the last position. So let's see if that goes into it nicely. 3125 divided by 625. It does. So we'll have, I'm going to have to do something like this. 4th root of 625, 4th root of 5. Then we have an x. We have a 4th root of x to the 3rd. That's not going anywhere because 4 doesn't go into 3. We've got y. So y to the 3rd. And a 4th root of y. 4th root of 625 is 5. So this is a 5. We've got an x and a y to the 3rd that are nice. And then we go back and get all the ugly stuff. We've got a 4th root of 5. We've got an x to the 3rd and a y. So all the stuff that works out nice gets to go in the front, but all the ugly stuff has to stay under the ugly radicals. Last but not least, we have to check and see if we should throw some absolute value bars around something. Does this need them? What needs them? Both of them, yeah. X to the 1st and y to the 3rd. Both need it. It's just the stuff outside of the radical bars, that radical symbol that's going to need those bars. All right, that was an interesting one. Cube root of 125. Cube root of a to the 12th. Cube root of b. What's the cube root of 125? 5. That worked out pretty nice. Now instead of writing them all out, can you tell me what the cube root of a to the 12th is going to be? A to the 4th. Yeah, you can use division. Now that doesn't mean that you can't write them down. If you want to write them down, cube root of a to the 3rd, cube root of a to the 3rd, cube root of a to the 3rd, cube root of a to the 3rd. Great method. Works every time. But that cube root of b, we can't do anything with that. That's a little 1. 1 doesn't divide into 3. Does this need absolute value bars? Nope. Cube root. Odd root. Number 10. Square root of 98. There's got to be a perfect square that goes into 98, right? You think of one? Something that will divide nicely into 98 from our perfect squares. 49 and 2. Good. So that'll give us a 7 and a square root of 2. Now, do you want to use division for the other ones, or do you want me to write them out as perfect squares? What's the square root of s to the 6th? S to the 3rd. What's the square root of t to the 8th? T to the 4th. And then we just, of course, put the nice stuff out in front. So we'll have 7 s to the 3rd, t to the 4th, square roots of 2. Absolute value bars? Yes? No? Part of it? All of it? Where? Just the S. Odd. Right there. All right, I'm going to rewrite 11 because I wrote all over that spot. Ooh, cube root of 432. Yikes. Y to the 7th. Well, I guess I'd try 8. Okay, but then there's still another 9 I could pull out of the other one. So, let's see. That was 2 cubed, and that would be, no, we can't take anything out of there that's a perfect cube. 27, 2 times. 27 times 8. 216, 432 divided by 216. How many of you would have caught that? How many of you would have said, yes, it's 216? Okay, so then you do what I did up there, which was I said, you know what? Let me check and see. I think 8 will go into this. So I've got a cube root of 8, and then I've got a cube root of 54. And then I notice, oh, 27 goes into 54. So this is still here. And things that sit right next to each other mean multiply. So 2 times 3 would give me 6 cubed roots of 2. So even if you didn't notice the biggest one when you start off, you could get there. Now, oh, 3 doesn't go into 7 nicely. How many times does it go into it? Twice. But we're going to have an ugly remainder of how many? 3 goes into 7 twice with an ugly remainder of 1. So now we put the pretty stuff out front. 6y squared. Ugly stuff under the radical. Cubed root of 2y. Absolute value bars with this one? Nope. Cube root? Cool. So that one took a bit. And we had a lot of numbers that we had to whittle that 432 down into. Oh boy, speaking of having to whittle, a fifth root of negative 729. Maybe we'll get lucky. Maybe it's a perfect fifth root. Huh? Let's check. Let's see. So for fifth roots, I have to punch in 5, math, then I have to go down here to number 5, because that tells the calculator fifth root. Negative 729. Oh, that's not nice. Well, then we better figure out a fifth root that might be small enough to divide into there. 2 to the 5th, 32, 729 divided by 32. Nope. 3 to the 5th, 243. Negative 729 divided by 243. Ooh, we found one. Okay, so 243 and 3. So we'll do the fifth root of negative 243 and the fifth root of 3. That way we can get the negative out front. 5 goes into 11 twice, but with an ugly remainder of 1. 5 goes into 8 once, but with an ugly remainder of 3. So negative 243 was 3 to the 5th power. So this will be negative 3, 5th root of 3, x squared, 5th root of x, y, 5th squared of y to the 3rd. And finally, we can put all the pretty stuff out in front and the ugly stuff in the back. Negative 3x squared y, 5th roots of 3xy to the 3rd. Does that mean absolute value bars? Ugly enough, right? Yeah, 5th root. No, we don't need absolute value bars. That one's tough. So it did some searching there to figure out what number was going to work with that. And I would say that's probably going to be the toughest page on the test. The first page down towards the bottom, that's probably going to be the biggest challenge for everybody. I don't see the second page as being quite as difficult. So, you ready to go on? Anybody need more time? 13. Simplify each expression, rationalize any denominators when needed, assume that all variables are positive. That's nice. That means we don't have to do absolute value anymore. We have enough to think of. Hey, this looks a lot like the Monday mistakes person. What should we do with that? Does 64 go into 4? Well, we better investigate that. So they're trying to hide something from us by not giving us one big fraction. They were hoping we would not notice that 4 goes into 64. And it does. How many times? Now, what are we supposed to do when we divide similar bases? What do we do with the exponents? Subtract. 5 minus 1 will be 4. 3 minus a negative 5 will be 3 plus 5. That's an 8. I think we just hit the jackpot. What's the square root of 16? 4. Square root of x to the fourth, what do we get? X squared. Square root of y to the eighth, y to the fourth. That's what they didn't want us to see. And again, you could separate these. Do square root of 16, square root of x squared, square root of x squared, square root of y 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 squared. You get the exact same answer. If you like that method and it works for you, just continue doing that. 14. Hey, there's a's and b's on the top. Over here, we made this a lot easier by doing the division first. We better investigate that. Let's see. Cube root of 5a squared b to the third c to the third over 3a to the third bc squared. Well, the 5/3, so there's anything we're going to be able to do with that. So that's going to have to stay. But we could certainly figure out what to do with our a's and b's and c's and take them off. So when we divide, what are we supposed to do with the exponents? Subtract. Or in this case, maybe you just want to cancel. You know, maybe you want to come over here, and I say that because there aren't any negative exponents. You might just want to cancel. You could certainly do, subtraction, but we could take 2 of these a's off of here, and that'll leave us with 1 down at the bottom. We could take 1 of these b's away, and that'll give us a b squared on the top. And then we could take 2 of these c's away, and that'll leave us with the c on the top. That's the exact thing you would get if you use subtraction. Because you'd say 2 minus 3 is a negative 1. I'm going to have to put that on the bottom to make it positive. 2 minus 1, 3 minus 1 for the b's would give us 2, and that's going to go on the top because it's positive. And then 3 minus 2 is 1. That's also positive, going to go on the top. But we've got a new problem. Even when we split this, we still have a radical in the denominator. But it won't take us very long to do it. You just have to make the index match the powers. What's the power of that little 3 that's down in the radicand there? If you had to put a power right here, what would it be? A 1. Well, we need it to be 3 because we want the cube root of something to the third power. So how many more do we need? We need 2 of them. So we're going to have to multiply by the cube root of 3 squared. And see, this morning when I did this, some people liked it when I wrote 3 squared down. Other people wanted to write 9. That is totally up to you. I'm going to do this as 3 squared so everybody can see the powers are going to match up. Because that'll be 3 to the third. We have an a to the first. How many more a's do we need to make this work? 2 more. Got to be 3's. So on the top, we now have the cube root of 5 times 3 squared is 9, so that'll be 45, a squared, b squared, c. And on the bottom, we have the cube root of 27a to the third, which is perfect, because that's 3a. And if you're saying, okay, but that gave us a really ugly numerator. I absolutely agree with you. It did. That is a very ugly numerator. But sometimes that happens. What we care about is we can't leave a radical in the denominator. That's what we care about. You might want to quick check and see any perfect cubes go into 45. 2 times 2 times 2. No, 8 doesn't go in. 3 times 3 times 3 is 27. No, that won't go in. 4 times 4 times 4 is 64. Well, no, I'm too big. It's not going to go in. We can check at the end, but that's it. That's all we can do. Well, 15 looks a little easier. How do we do 15? FOIL. Yeah, FOIL. Now, if it's a special pattern, we might not have to do all of FOIL. So look at this and see, ooh, that's a 7. That's 2 square roots of 3, and one's a plus and one's a minus. That means I don't have to do the O and the I. I can just do foo instead. Because they're going to cancel each other out. So first times first is 49. Last times last is minus 4 square roots of 9. And you have a light bulb moment and you go, oh, that's the 3. 49 minus 4 times 3 will be minus 12. Hey, that's 37. Took two rather weird looking binomials and got ourselves a very nice integer answer. That works. 16. Can we distribute that too? Nope. If there's addition or subtraction in parentheses, you can't distribute. What we have to do is write this down twice and do FOIL. Because this is not going to be a plus and a minus situation. We're going to have to do all of FOIL. So first times first, square root of 121. Outside times outside, plus 3 square roots of 11. Inside times inside, plus 3 square roots of 11. Last times last, plus 9. The light bulb moment, the square root of 121 is 11. And we can put these two middle ones together. And then you realize 11 and 9 is 20. Now we can't go any farther because you can only... All right, so we ran out of time in fifth hour to go over these last few. With number 17, we had to multiply the top and the bottom by the conjugate. And the conjugate is using these two terms, but with a different sign in the middle. So we had the square root of 2 minus 7. We multiply by that conjugate the square root of 2 minus 7. And in the numerator, we have 1 times the square root of 2 minus 7. That's right here. But in the denominator, we realize if we do FOIL, outside times outside and inside times inside are going to cancel out. So all we really have to do is first times first and last times last. So square root of 2 times the square root of 2 is the square root of 4. Positive 7 times negative 7 minus 49. We have a light bulb moment and we notice that's a 2. So 2 minus 49 is negative 47. And then, as I said in class, the book will not leave that negative in the denominator. They like to use that for the numerator. So what they do instead is take it off and distribute it across the top of the fraction. So that'll be negative square root of 2 plus 7 over 47, or 7 minus the square root of 2 over 47. I'm going to take any of them. You know, you could have stopped right here and said square root of 2 minus 7 over negative 47, because that's right. The other two are just, well, it would be type errors for their person who's going to punch this into the word processor when they put it into the book. So it's easier for them to distribute that. Number 18, we see that these are both square roots, so we would keep the square root and we would take 3 times 27 and get 81. And then we have the same bases in x and x, so x to the 4th times x to the 6th. When you have the same bases, you add the exponents. And then the square root of 81 will give us 9. And the square root of x to the 10th, you could always write out the square root of x squared, 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 the square root of x squared. But most of you by now realized, you know, dividing will make that go faster. And 10 divided by 2 will give you x to the 5th. And no absolute value with bars with these. This told us to assume all variables were positive. Number 19, we're supposed to be able to add and subtract. The only way we're going to be able to do that is if we can get the radicals to be like radicals. So the educated cheat is to go to the smallest radical that you see and then try to make the others match. And I think, well, if we're going to be able to add and subtract these, they all have to be the square root of 3. So I better see what I can get with the square root of 3 for 192. Well, 3 goes into 19 6 times with the remainder of 1, and 3 goes into 12 4 times. So that'll be the square root of 64 and the square root of 3. And that's 8 square roots of 3. Then for the 27, we have a 4, and that'll be the square root of 9 and the square root of 3. Well, the square root of 9 is going to be 3. So 4 times 3 will give us plus 12 square roots of 3, and then minus 2 square roots of 3. And now we have like radicals. They all have the square root of 3. So 8 of them plus 12 of them is 20, and 20 minus 2 will give us 18 square roots of 3. Like radicals. Number 20, with this one, really, there is no advantage to changing this to the 4th root of 7 halves. It's not going to reduce any further. So we have the 4th root of 7 over the 4th root of 2, and we realize, really, this problem is about rationalizing the denominator. this is a 1, and we can't leave that down there. So we're going to need 3 more of those 2's, which is 4th root of 2 to the 3rd, but what you do to the bottom, you have to do to the top. Now you could certainly figure out that 2 to the 3rd is 8 if you want to, and use an 8 instead. So up on the top, we'd have 7 times 8, which is the 4th root of 56. And on the bottom, we have the 4th root of 2 to the 4th, or the 4th root of 16, which is just 2. And then you could check and see. 2 to the 4th is 16. 56 is not divisible by 16. And you could try 3 to the 4th, and you're going to see, well, that's already too big here. That's not going to work. So 4th root of 56 over 2. Because technically, this is the 4th root of 2 to the 4th, and these are inverses of each other, so they will drop out. And down here with number 21. Number 21 has multiplication. And because these are both cubed roots, we can go ahead and multiply, but we need to take integer times integer, which will be 14. And then cubed root of 16 times 5, so you quickly get the math for 80 there. And then we would have y to the 12th, because when you multiply those similar bases, you add the exponents. But then hopefully you realize, hey, with that cubed root of 80, that's the cubed root of 8 times the cubed root of 10. And then we'd have the cubed root of y to the 3rd, 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 and that would give us a grand total of our 12 for the y to the 12th. And then we'll have a 14 and a nice 2, an ugly cubed root of 10. We'll have a y, a y, a y, and a y. And that will give us 28 y to the 4th cubed roots of 10. And that's as simplified as that is going to get. We have no more perfect cubes that will go into 10. That's the end of the practice test for the Chapter 6 Concept Bite and Section 6.1, 6.2, and 6.3.